Hello everyone, I'm Mitigur Buz. I'm here to present Generalized Sampling for Metric Learning, our collaborative work with Ozan Şener and Aydın Alatan. In deep metric learning, we aim to train an embedding function that brings similar samples closer together in the embedding space while pushing dissimilar ones farther apart. An essential goal is to make sure that this learned behavior generalizes to unseen classes. We often rely on convolutional neural networks paired with global average pooling to craft our embedding functions. However, global average pooling has its limitations. It treats all semantic information equally, which can lead to poor embeddings due to irrelevant details. Additionally, traditional deep metric learning frameworks lacks an explicit mechanism for handling unseen classes. To address these issues, we propose generalized sum pooling, a learnable and generalized version of global average pooling. We redefine global average pooling as a solution of an optimization problem. With generalized sum pooling, we introduce learnable prototypes and assign them partial weights. This way, the pooling layer learns to choose and weight the subset of the features. Crucially, we rigorously show that the global average pooling is a specific case of our proposed optimization problem for a certain realization. Our proposed optimization problem closely follows optimal transport-based top-K operators, and we utilize its literature to solve it. Predominantly, we derive a closed-form matrix inversion-free gradient expression that enables efficient backpropagation through generalized sampling. This makes our approach scalable and computationally efficient. Here is how our method integrates into a deep metric learning framework. We designed a synthetic empirical study to evaluate global sampling in a fully controlled manner. In this study, we simulated a convolutional neural network's output using trainable tokens. Each class has its set of learnable tokens, and we also have a shared token set. To create a sample feature map, we randomly sampled from both class-specific tokens and shared tokens, with the ratio between them varying for each sample. We then obtained global representations using both global average pooling and global sum pooling. We visualize the geometry of the embedding space along with the deep metric learning performances. With global average pooling, we observe overlapping class convex hulls resulting in poor deep metric learning performance. However, when we applied generalized sum pooling, the results were slightly different. We found that it effectively separates class convex hulls, indicating that it can learn to disregard irrelevant tokens. Let's now address a critical aspect of deep metric learning, generalization to unseen classes. Note that classifying the labels as prototypes is a degenerate solution and fails to generalize to unseen classes. To overcome this challenge, we introduce a zero-shot regularization loss that explicitly enforces the transferability of local features. Here is our key insight. As we compute the pooling weights, we also obtain a histogram of the prototype assignments, let's say attribute vectors. Given label embeddings, if we split a batch into two with disjoint class sets, then the predictor mapping the histograms to the class embeddings for a batch should excel at predict the class labels of the other batch as well. In other words, if the prototypes are transferable, we can leverage the predictor fitted to one split to transform the histograms of the other split. We translate this concept into a differentiable layer, leveraging the closed form solution of ridge regression. Now, let's see how this concept performs in practice, specifically on the CIFAR10 dataset. With zero-shot prediction laws, prototypes tend to align with specific classes, but with our method, we attain shared representations. When we quantitatively assess the generalization ability, we saw that prototypes learned using zero-shot prediction laws consistently exhibit significantly better generalization performance. This result is further confirmed qualitatively when we inspect the prototypes representing the images. With our approach, images are represented as a combination of them. Finally, let's dive into our experimental results. We conducted comprehensive evaluations on four popular metric learning benchmarks. In our comparisons with other pooling alternatives, our method consistently stood out as a superior pooling mechanism, demonstrating better improvement margins. For deep metric learning benchmarking, we employed two settings. First, we used the BN inception backbone with the metric learning reality check setting, which helped us focus exclusively on our method's impacts while reducing confounding factors. Our method, when applied alongside well-established and state-of-the-art loss functions, consistently elevated their performance. In the second setting, we switched to the ResNet 50 backbone and adopted the conventional evaluation setup. Here, we directly compared our method with state-of-the-art approach. We found out that generalized sampling consistently improved the applied methods, even setting new state-of-the-art results. Thank you for watching. We are here to answer any questions you may have, so please don't hesitate to reach out.